Boom. Okay. To go farther, looking at evolutionary patterns, we've got to start looking a bit at the history of the Earth and the land masses and ocean basins on it. And to do that right, we have to backtrack a little bit and take a little step into geology, which is not something we have a department of here at UCA, and look at a theory that revolutionized the earth sciences as much as Darwin's theory revolutionized the life sciences. This is the theory of plate tectonics, and it goes a little something like this. It starts with a guy named Alfred Wegener, no relation. Don't spell our names the same way, anyhow. Wegener had the kind of mind that just does not neatly fit into one little disciplinary box. He was a meteorologist. He was a pioneer in the use of weather balloons, uh, sending weather instruments up in a balloon to measure conditions in the upper atmosphere. He was a geophysicist. He got his PhD with some research into very old medieval astronomical data. And he got interested in the seemingly crazy possibility that the Earth's continents had not always been in their current positions, but in fact had shifted over time. When he was reading about the distribution of animal and plant fossils in far-flung places on the Earth. And the theory that he came up with, which he first published in 1905, starts with about roughly 250 million years ago, the Earth's continents are glommed together into a single supercontinent called Pangaea. Gaea, by the way, is the Greek root for the earth or the land. Pangaea. Pan is Greek for all, so Pangaea, all the earth. And that's all the Earth's continents stuck together in one big landmass. And Pangaea formed about 250 million years ago. Before Pangaea, the continents were separate. And in fact, we now think that roughly on a cycle that lasts roughly 500 million years, we have supercontinents break up, and then the pieces coming back together to make a new supercontinent. It's called the Wilson cycle, but that's not something we're going to get into here. For right now, let's just say that the continents came together ending about 250 million years ago to form this supercontinent called Pangaea. Pangaea began breaking up roughly 200 million years ago. Didn't all break up at the same time. It took a very long time for it all to break. But the first break split Pangaea into a northern half and a southern half. The northern half we now call Laurasia, and the northern half consisted of North America plus Europe and most of Asia. The southern half we now call Gondwana, and Gondwana consisted of South America, Africa, India, which used to be a separate little continent of its own, Antarctica, and Australia, plus a few little bits and bobs like New Zealand, Madagascar, and New Guinea. Both of those halves then fragment further to give rise to the continents that we recognize now. What was some of his evidence? Well, it looked like this. He looked at fossils from about the time that Pangaea was breaking up. What you see here are fossils of a fern-like plant, technically not a fern. If you saw one, you might think it was a fern, and then you might be a little surprised to find that it's got seeds. But it's the plant Glossopteris, and it's got distinctive leaf vein patterns. So if the leaves are preserved, you can recognize it immediately. On the left is one from Antarctica. On the right is one from India. That's this double mid vein right there. And then you can see the little parallel side veins coming off like that. There in Antarctica, you have this double central vein and then the side veins coming off in that direction. And over there in the center, that's some Glossopteris leaf fossils from Australia. Notice where these are from. They're found in Antarctica, in India. If you were curious, by the way, Antarctica is something like 98% covered in ice. The 2% that isn't includes rocks with a fair number of fossils in them. You can find fossils from many different time periods in Antarctica, even though we can only see 2% of the rock that makes up Antarctica. The rest is covered in ice. There's at least one dinosaur that has turned up in Antarctic rocks, a thing called Cryolophosaurus. So, yeah. And there are these fossil leaves that have turned up in Antarctica, India, Australia, never North America, Europe, or Asia, except for India. These are synapsids. They are not fully mammalian, but these are relatives and ancestors of the modern mammals. Lystrosaurus up at the top, rather odd critter that had a pair of tusk-like teeth up at the front to presumably dig with. Synagnathus down there below looks a little bit more like a carnivore, more upright posture. You can tell they're related to mammals because they've got different sizes and shapes of teeth, like you. These have incisors, canines, premolars, and molars. They've got a more upright posture. They're not fully mammalian because you can tell they're not fully mammalian because they've still got lumbar ribs. These ribs back here along the back, a true mammal would not have those. There's some various other differences, but anyway, this is a group called the synapsids that's related to mammals, but not quite mammals. And then, whoops, sorry. And then that's an odd little reptile. Maybe the body might be about a foot long, the tail's a bit more. Little lizardy thing that seems to have been adapted for aquatic life, life in the water. We call this Mesosaurus. And here's why this matters. Synagnathus turns up in South America and Africa. Lystrosaurus turns up in Africa, India, and Antarctica. Mesosaurus is only found in South America and Africa. Glossopteris, that seed ferny type plant, is found in all of these: South America, Africa, India, Antarctica, and Australia. And here's the thing, they all date from the time when Pangea existed and was just about to start breaking up. If you only found one of them, you might assume that they got to where they got by means of dispersal. Like, we know that Glossopteris has seeds, so maybe it evolved in South America and its seeds washed out to sea and drifted to Africa, and from there drifted to India or something like that. Maybe that would work, but that doesn't explain how something like Lystrosaurus could disperse in the same way. Or Mesosaurus, the little freshwater swimming reptile, maybe that could swim across an ocean. Certainly Synagnathus can't. So you have these different taxa, they've all got this overlapping pattern of distribution. You know, there's none except Glossopteris that's found on all 5 of these continents, but they're all found on some subset of it. And they're found right when Pangea exists and right as it's starting to think about breaking up. And none of these have ever been found in North America, in Europe, or in the rest of Asia. So the idea is that these taxa must have evolved in South Gondwana, spread through South Gondwana, and then South Gondwana broke up. Um, and now their fossils have drifted off onto different continents, but the land where we find these fossils used to be connected. I trust that makes a certain degree of sense. You can do this with living organisms as well. On the left, that's Nothofagus, the so-called southern beach, and living Nothofagus turns up in South America, southern South America, and in Australia and New Zealand and New Guinea. These little asterisks over here are places where fossils have been found. So they used to be found in much more of Australia. And also right there, that's a fossil that turned up in Antarctica. So again, you've got Nothofagus living in South America, Antarctica, Australia, New Guinea, and New Zealand, nowhere else in the world. And the fossils follow the same pattern. Why? Lungfish are so dependent on an accessory breathing organ, a lung, okay, that they have to gulp air. Their gills are not enough to get them all of the oxygen their bodies need, meaning that lungfish are the only fish that I know of that can drown. You can kill a lungfish if you don't let it rise to the surface and gulp air. There's an African lungfish at the left. Up at the top, that is an Australian lungfish, and there's a South American lungfish down at the lower right. There again, that's the three living species of lungfish, and they're found only on continents that used to be next to each other, according to Alfred Wegener. Africa, Australia, South America. Now, you could argue that, well, maybe the continents haven't been moving. There have always been oceans between them, and lungfish just swam. Maybe, but modern lungfish, A, live in fresh water and would not handle the ocean very well, and B, they're not strong swimmers. They'll spend most of their time on the bottom. Oh, there are tuna and sailfish that can cross oceans. These are not they. Lungfish are not built for high-speed oceanic crossings. It seems very unlikely that they could disperse that way. And there's more. Conifers in the family Araucariaceae, mud minnows in the family Galaxidae, ratite birds, that's birds with a flat breastbone, which is tinamoos and cassowaries and ostriches and emus and rheas. Let me see, there's certain families of earthworms and flowering plants in the family Proteaceae, which are shown here. They're all endemic to the continents that Wegener thought must have once been connected in that southern half of Pangaea that we now call Gondwana. So these are all Gondwanan endemics. So at the top left, Protea cineroides is the national flower of South Africa. Down at the bottom left, that's an Australian Protea or Proteacean, and there's a South American Proteaceae at the top right. None of these naturally turn up in North America, Europe, or most of Asia. Now, Pangaea would have rifted into a northern half and a southern half, and you've seen a number of examples of living taxa that are unique to that southern half that we call Gondwana. If you're wondering about taxa that are unique to the northern half, well, there's a lot that you'd know. Oaks, sequoia trees, sequoia redwoods in general, including bald cypress is the one that we get around here. Bears, great example. And flowering plants in the Cornacean family. The Cornaceae is dogwoods and tupelos. Up there at the top left, there's American flowering dogwood. I know you've seen that before. There's a nice one growing right outside the back entrance to Lewis. At the top right, there's an Asian dogwood, Cornus cusa. Bottom right, that's a European dogwood that's actually a shrubby form that actually makes edible seeds. That's the bog bunchberry. And so this family of flowering plants is all endemic to Laurasia, the northern half of Gondwana. So Wegener put the continents together and found that the distribution of a lot of these groups of animals and plants actually matched up with each other if you put the continents together. The same thing happened when he put the continents back together and looked at geological features. Imagine you've just broken a fancy dish that has, you've broken it into pieces and there's some kind of design on the dish. Maybe it's like one of these blue and white designs that my grandmother used to love. And let's say you need to put the dish back together. Well, you could fit the outlines of the pieces together; those should fit. But you will also notice that if you put the pieces together right, not only will the outlines match up, but the designs on the pieces will, right? One half of the little girl in pigtails will perfectly match the other half of the little girl in pigtails, or one half of the vase of flowers will match perfectly with the other half of the vase of flowers, or whatever it is that is on the design on that plate. Similar logic applies to putting the continents back together. One of the things that we have, for example, is if you put the continents back together, the coal deposits of Eastern North America, including, Kentucky, West Virginia, and also a little bit in Arkansas, although that's almost gone now, and the coal deposits of Western Europe in places like Germany and coal in Northern Africa, all of those match, all of those come together. Down here, glacial deposits. We'll look at this in more detail in a minute, but rocks that have been laid down by glacial activity look very distinctive. And we find glacial deposits here in Africa, Australia, Antarctica, South America. Put the continents back together and they all match. They all fit together. Beds of desert sandstone and gypsum in North America and Siberia, they match. There are mountain ranges like the Appalachians here and the Scottish Highlands here and the Kiel Mountains of Norway. They match if you put the continents back together. Here's a closer look at that evidence of glaciation. When glaciers pass over a landscape, you can tell. They will tend to grind up the rock that they're passing over. They'll tend to dump it into the ocean in the form of lumps of rock mixed with very fine sediments. And as a glacier moves over the land, it tends to leave scratches. You're familiar with glaciers, I trust, enormous rivers or sheets of ice very slowly grinding their way over the landscape. Well, at about the time that Wegener thought Pangaea had existed, there was a glacial episode, and there were these glacial deposits scattered all over the Gondwanan continents. And when you move them together, the glacial areas match, right? We've got this one continuous band of glacial rock, and you can tell what direction the glaciers were moving because a sheet of ice grinding over a big chunk of rock leaves scratches. They're called glacial striations, and we can see these forming today in places like Alaska, where glaciation is still going on. And the direction of the striations tells you the direction in which the ice was moving. And so when you put the continents together, all of these directions line up. They're consistent with an ice sheet forming where the South Pole used to be and spreading out from it in all directions. That makes sense. Wegener put this out first in 1908, I think, in a book called The Origin of Continents and Oceans. And he put out several editions of it until his death in 1930. He actually died on the Greenland ice cap, taking part in a polar exploration mission. He'd gone off on a dangerous mission to deliver supplies to a detached group of researchers. And he succeeded in that, but then got lost on the way back to base camp and has never been found. So, yeah, died in the field. And at first, his ideas tended to be dismissed because it sounds nuts. The idea that you could have something as big as a continent moving. I mean, North America is roughly 3,000 miles wide and, I'd say on average about 25 miles deep. You know, what force can move something that big? What started to happen was that in the 1950s, there was increasing exploration of the ocean floor, led by ships like the Glomar Challenger. The Glomar Challenger was actually a Black Ops project to try to capture wrecked Soviet submarines, which they actually did. That was the real mission. But as part of their cover, they actually went out and drilled a lot of ocean rocks and took a lot of samples and started exploring what the bottom of the ocean looked like for the first time ever. And their discoveries of what ocean basins look like at the bottom led to the formation of modern plate tectonic theory by 1965. And it goes a little something like this. Okay, we're on a continent. This one happens to be California. San Jose is right there. San Francisco is kind of off the map, somewhere about there. Monterey is right about there. The coastline is right here, but geologically, the coastline is not necessarily where the action is, because the coastline is always subject to shifting as sea levels rise and fall. And as in some areas, I guess it goes on like that. Sea levels rise and fall for reasons we may not get to talk about. Land rises and sinks, or it can in some places. And the position of the actual coastline tends to shift over time. In fact, if you drive along the coast here, you can actually drive the coastal roads and you're on the top of a cliff that overlooks where the waves are breaking. And then about a mile away, you can see another cliff inland, which is where the waves were breaking when the sea level was higher. Now you get these, they're called terrace deposits out there. So the position of the coastline, that changes. What doesn't change is that off the away from the coastline, anywhere from maybe 100 miles thick to maybe only a few, we have this zone that is relatively shallow. I mean, it still may be, it still may be several hundred feet, which is pretty deep. It's deeper than you could dive. But we have this relatively shallow and flat zone called the continental shelf. And then the continental shelf drops off. If you were walking, you'd feel the continental shelf as being fairly flat. And at the edge of the continental shelf, you'd start descending. It's not as steep as it looks here. It's maybe 2 degrees decline. but you start going down the continental slope, and the edge of the shelf is what marks the real permanent edge of the continent. So there's this shelf. The slope slopes down here, and then the slope goes down to the abyssal plain, which might be 10,000 feet deep or more. In the Pacific, typically it might be 20,000 feet. If you match up the outlines not of the coasts, but of the continental shelves, you get this. You get an almost perfect fit. The pieces fit together very precisely. Some computer simulations have shown that basically there is virtually no way, there's a 1 in a umpty-ump cajillion chance that this kind of fit could be the result of chance. By far the best explanation is that the continental shelves fit together because this is how the continents themselves used to fit together, like that. Our model is that both continental and oceanic crust are, okay, the Earth's outermost layer, the Earth is like an ogre. They have layers, like an onion. And the outermost layer is the crust. That consists of solid rock. If you could shrink the Earth down to the size of an apple, the crust would be about the thickness of the peel. Below the crust, there is a very thick layer of rocks called the mantle layer. Within the mantle, there is a core, and the core is subdivided into the outer core and the inner core. And I think I just recently read they now have some evidence that the inner core may be subdivided into the inner core and the outer inner core, or something like that. So it's a bit of a simplification there. The mantle is, you'll hear people say that it's liquid. It's not really. It's solid rock, but it's under very high pressure and it's very hot. And rock under very high temperature and pressure sometimes forgets that it's rock, and it starts flowing. You could think of it as being sort of like one of these substances, like, think of peanut butter. Is it a solid or a liquid? Well, you can't pour it, right? You can't, if you drop a blob of peanut butter on the countertop, it doesn't flow. It doesn't spread out the way that dropping a blob of honey or syrup on the counter does. So it's not really a liquid, but if you apply a little bit of force to it, like with a knife, you can spread the peanut butter and you can cause it to flow. So this is not a perfect analogy, but you could think of the upper layer of the mantle as being kind of like a giant ocean of peanut butter, with the oceanic crust sitting up on top of it. And that upper mantle layer is called the asthenosphere. That's Greek for the weak layer, weak as in not strong, asthenos. And our current model for what is moving the continents is that continental and oceanic crust, both the rocks that make up the continents and the rocks that make up the floors of the deep ocean, are literally floating on the upper mantle because they're just a bit less dense than the upper mantle is. And over very long periods of time, again, the asthenosphere is not really a liquid, but it does flow. And convection in the asthenosphere is probably, people debate this a little bit, we'll go with convection in the asthenosphere as the driving force that moves the continents around. And in point of fact, we can actually measure that using GPS technology. Your phone is not quite accurate enough for this, but with more sophisticated ground receivers, we can measure the distance between any 2 points on Earth down to the millimeter. very useful if we want to send a cruise missile right up Saddam Hussein's car tailpipe or something like that. We can pinpoint places on the Earth extremely precisely, and typical measurement as to how fast plates are moving usually comes in between 2 and 20 centimeters per year. That's roughly somewhere between the speed that your fingernails grow and the speed that your hair grows, roughly. So, what's going on? Continental and oceanic crust together form what we call the tectonic plates. You can see that we are on the North American plate. Down to the south, there's a smaller plate called the Caribbean plate. South America, plus a big chunk of the Atlantic Ocean floor, is on the South American plate. To our west, we've got the Cocos plate and the Nazca plate. And by the way, right about here at the triple junction of the three happens to be where the Galapagos are. There's a small plate called the Juan de Fuca plate off the coast of Northern California up to British Columbia. Most of the Pacific is one big plate. Australia is on a plate. Eurasia, Europe, and most of Asia are on one plate. The Eurasian plate was actually assembled out of earlier smaller plates. So it's not really considered a separate plate now, but about 500 million years ago, there actually was a China plate, which I think is funny if nobody else does. So anyway, so yeah, continental and oceanic crust together form these plates. What's moving them is thought to be convection in the asthenosphere. Remember, convection is that circular movement of a fluid under heating. If you've ever boiled water on a stove, you might have been able to see bubbles rising and cooler water sinking. Certainly, if you put a few rice grains into water as it boils, and you'll see the rice grains rising, coming to the surface, and then dropping back down. That circular motion is convection. The edges of those plates are often associated with earthquakes. This is data from 1980 to 1990. Younger data would show exactly the same pattern. Every one of these dots is the epicenter of an earthquake of magnitude 5 or more. And you can see how they almost perfectly trace out these plate boundaries. The rim of the Pacific plate and then the Nazca plate up here is sometimes called the Ring of Fire because there's so many earthquakes and volcanoes along here. So, this is the Ring of Fire. You can see there's a bit fewer of them, but you can see earthquake activity down here in the middle of the Atlantic. There's a few areas that aren't associated with plate margins. Here's Hawaii, and we'll talk about what Hawaii is a little bit later. And you can get some areas like up here. India is still crashing into Asia, so you've got a lot of earthquake activity here around the boundary of what used to be a separate plate. But yeah, the vast majority of earthquakes and volcanoes take place along plate margins, along the edges. And as I mentioned, ooh, look, it's computer animation. GPS can be used now to measure directly how fast the plates are moving. There's a GPS satellite and a high-end ground receiver right there. And as I mentioned, the speed is between 2 centimeters and 15 centimeters a year, depending on where you are. And again, that's roughly somewhere between the speed of your fingernails growing and the speed of your hair growing. Let me see. Somebody shoot me this in the chat. What time is it? I'm sorry. This cold is making me sick, and I may have to end this early, but I'm trying to pace myself. Okay, the time is 10:50. Okay, now is a good time for a break. And I'm going to need a slightly longer one. I'll see you folks at 11:10. And I will stop the recording now.